December 23rd, 2019. Guys, what you're looking at is a pump curve for a water CLVK 500 gallon per minute pump. And it's got some pretty useful information on here. And the problem is that most individuals do not really understand how to read these things. So I'm going to go over it and show you a couple of other things. Also, what I'm going to do is I'm going to cover helicopters again, and some of you guys in the volunteer departments and rural structure departments probably getting sick of hearing me talking about this. And there's a reason that I keep talking about the helicopters. And one of those reasons is that for us in the wildland environment, these guys right here demand the greatest amount of flow in equivalent gallons per minute. These guys move a tremendous amount of water very quickly and over a greater distance than any engine with a nozzle can. So I'm going to talk about that, and then I'm going to talk about how the structure world is really no different when you've got long hose lays and you've got an area such as this one here in my local area, to where a hydrant will stop here, but yet you'll come down all the way to this end here, 3/4 of a mile away, and you'll have structures. And if anything goes up over in there, because we're so remote, you could end up being a good hour and a half from a water tender coming from the nearest town to help you. And our town only has one water tender. The next closest one is about 10 miles away. And so the point that I'm trying to make here is that wildland and structure both have the same properties, the same unique water delivery problems, the same logistics problems, and then they also have the same aspects that you need to take into account for. So if you've got an engine at any point in here, especially down at the end of when you're attacking a structure fire, depending on the size of the structure and what its percentage of involvement is, according to the National Fire Academy formula that they use that establishes minimum flow in gallons per minute, you could end up having the same or similar amount of flow as it is when you get back to a helicopter with a bucket. So everything that moves water from one point to another has an equivalent gallon per minute rating. If you look at a situation and you say, well, I only need to move 200 gallons a minute or 250 gallons a minute, and I've got a 500, 750, 1,000 gallon per minute pump, you might be thinking to yourself, well, I'm covered. And I'm basically here to tell you, not so fast. It doesn't work that way like you would think. So real quickly, we'll talk about the wildland aspect of what I deal with, and then we'll move into the structure. So for the water tender that I operate, it's got this pump, the CLVK 500, and all fire pumps that are designed to move 250 gallons a minute or more have to meet 1901 NFPA standards, especially under NFPA 1906 for the wildland environment. If it moves 250 gallons a minute or more, it has to meet 1901 standards, which means that you will follow the NFPA ratings, and that is that a fire pump has to deliver 100% of its capacity at 150 PSI net pump pressure. And it has to be able to produce 70% of its rated capacity. So that means 70% of 500 gallons a minute is 350 gallons a minute. And it has to be able to deliver that at 200 PSI. And then it has to be able to move 50% of its capacity, so half of 500, so 250 gallons a minute at 250 PSI. So now that I've explained what this is, going into a little bit more detail here. Over here, these are revolutions per minute tick marks on the impeller. So you can see that you can expect to have approximately at 500 gallons a minute at 100% capacity around the neighborhood of about 4,800 revolutions a minute on the impeller. That's not what your engine's going to be doing. Your engine might only be spinning at about 11, 12, 1,300. It depends on the gear ratios. My gear ratio is a 3.40, and then it's got a PTO ratio of 1.37. So that'll be another video for a later time. But as you start moving up in engine speed, the impeller speed climbs, but you lose in your gallon capacity, even though that your pressure is going up. Um, and that's standard. So you can get to a point to where if you start reaching the 300 psi mark, you're only going to be moving about 125 gallons a minute on this particular pump. And if you go up to 350 psi, which is the max for this particular pump, you're only expected to get about 16% of the volume, or 80 gallons a minute. So now that we've given a basic overview of what this pump curve is, let's go into the structural aspects for the equivalent of the wildland environment from the structure side. So if we've got a structure, and let's say that it's 40 feet in length and 60 feet wide, or vice versa, and you've got 30% of involvement, and there's only one floor to this building, the minimum flow that the NFA wants you to begin flowing is 240 gallons a minute. So you think to yourself right off the bat, okay, well, that's not too bad. I got a 500 gallon per minute pump, so I can do that with ease. Now we have to look at another critical factor. So we've got 240 gallons a minute, but again, we've got to do that through 3,900 feet, because remember, that's the closest point to the hydrant, which is right there. You do have a little bit of downslope here, but the downslope is only about, the lowest point is about right there. And so that's at about 2,176 feet away from the hydrant. So if you back this off and just go 2,100 feet, you still have roughly another 1,800 feet to supply water to. So let's see where that 240 gallons a minute at 250 psi is going to, how far that's going to get us, because that's the trick. That's what you have to start looking at. So if you try to go any greater than that, think of this line as a vertical wall. If you move up in pressure, this wall is a limiter and starts to move closer and closer down to zero. So you have to try to figure out what size hose, how many, a parallel line, multi-line drop, 2, 3, 4 lines, or if you're going to do a relay operation. So this is where understanding hydraulics and friction loss really comes into play. So if we go back to our friction loss calculator, and most VFDs like to use 2.5 inch hose. They don't like to pull out the high ball. So let's say we've got the desired flow of 240 gallons a minute on a 2.5 inch, and it's 11.5. So let's say we got 2,100 feet. So let's see what that does. Well, that's already 240 psi. And 2,200 feet is going to put it at 253. So you're not going to get any more than 2,100 feet. And the 2,100 foot mark, as I said, is down here at that intersection. So you're already maxed out for a 500 gallon per minute pump. So now let's go ahead and look at something like this. Let's say you get a 1,000 gallon per minute pump. Well, you can see right here that it's 1,000 gallons a minute at 150, and then a 1,500 gallon per minute pump at 150. This is industry standard. So let's say that you got 1,000 gallon per minute pump. The 50% is still 500 gallons a minute at 250 psi. So let's see what would happen if you start falling into that trap of, well, I can move 500 gallons a minute. So now look where you're at, 2,200 feet. Now you would need 1,100 psi. So you're not going to get anything. It's 50 psi per stick of hose now. So you're probably only going to get, where did I go? 500. So you're only going to get 500 feet off of a 1,000 gallon per minute pump if you try to move 50% flow through that thing. So where does that take us? Well, that 500 foot mark brings you closer to the hydrant, not closer to the house. And so this is a common problem that a lot of people that don't understand hydraulics and flow, you have to be thinking about. So the best thing to do here is you can have the bigger pumps, and bigger pumps are better in terms of being able to deliver the flow demand, but the only option that you have in increasing the flow means that we need to increase the hose diameter. So for us in the wildland, the largest hose that we carry in the caches and in the national fire cache is 1.5 inches. Well, that renders this operation basically tango uniform, because you're not going to be able to move that kind of water to feed these things, to feed the helicopters nonstop with an 1.5 inch hose. You would have to run like 3 and 4 lines, the same distance as a single line of 2.5 inch. So what we really need in the wildland environment is 2.5 inch. And for the structure counterpart, you guys can use 2.5 inch, especially in the volunteers and the rurals. But a 2.5 inch hose, you could do it. You would just have to put, an engine or a couple of engines in between here. Usually every 1,200 feet, that's the average. So if you did 1,200 feet, so let's say you go right about there, you put an engine, and so then you go to 24. So there's another engine. And then you would need at 36, which would be somewhere out in here, there would be a third engine. So you would have to have 3 engines in a relay to use 2.5 inch hose for this to go to a couple of nozzles if you had a structure up here. So that's why understanding flow and water delivery and logistics and how to calculate it is vital, because it cuts into the response time. And everybody knows that response time is vital, because the faster and the more efficient you are, the bigger the dent you can put in your fire. That's no different than what I have to deal with this. This is my equivalent to dealing with multiple nozzles on a structure fire. So the fastest, easiest, simplest method is to go from the hydrant, single line, straight out, be done with it. But you start from where the end is and you work your way back. No different than me. If we've got, you see this tank is sitting here up on top of a hill someplace. I always talk about that. You can see the line down here in the bottom plumbed into the bottom of it. Wherever this is, we have no choice but to shuttle water and bring it to this tank, and we have to do it in a manner to where this helicopter is not sitting waiting for us. So this is our nozzle, and it's no different than this over here. And so anyway, that's it, guys. Have a good afternoon, and Merry Christmas.